And welcome back, everybody. This is our first video for this third topic in the contamination course, and we're looking at dimensions. So we want to discuss the dimensionality of those advection dispersion model. So here's a quick illustration. I mean, the problem with the dimensions, right, is that in aquifers, typically we always think of the spreading of mass or contamination in at least 2 dimensions, sometimes 3, but mostly in 2 dimensions. And this is sort of the planar view of the aquifer, so the top view of the aquifer. So there's always sort of a regional flow, right? The x direction would be your main flow in the down gradient direction, which would be your x direction. And then you also have spread in the y direction, or the perpendicular direction, where mass by dispersion, right, or by diffusion and dispersion, sort of spreads in that other direction. So in the aquifer plane, surface. Okay, so here's an illustration where you can see this main direction, u, and then the cross direction here in the y direction. So in the y direction, there's no velocity, obviously, right? There's no advective flux, but there is still dispersion spreading. So now you have that 2D concentration distribution that looks like an ellipse. And the reason, okay, so here's the equation in x and y. So this is just the diffusion equation or dispersion equation. You can see there's no velocity here, and here is the same equation with the advective flux added. So now we have a regional flux in the x direction. Okay, so here if we look at the peak equation, the equation for the peak of the distribution, you can see that in 1D the peak concentration was given by m over a square root of 4 pi dt, and in 2D you can see that now the area is replaced by the depth of the aquifer. So we assume that there's an instantaneous mixing throughout the depth of the aquifer, so which would be true for like shallow aquifers, let's say. So m over z instead of the area, and then you can see that 4 pi t is moved outside of the square root, right? So now the peak is going to decrease as a function of 1 over time instead of 1 over square root of time. So the scaling is going to be very different, and we'll discuss this in a second. And then you can see here that now we have the dispersion in both the x and the y direction, as opposed to only the x direction here. I mean, it's a 1D problem. And again, in the parentheses, so remember now if we put the entire equation, dt, right? So now we have this for the x direction, and we have a similar one for the y direction, but again, in the y direction, there's no velocity, there's no net advective flux, so we only have the equivalent of a diffusion equation in the y direction. But notice that in the exponential, the second direction also appears. Okay, so this is all the analytical solution for the advection dispersion equation in 2D. Now, if we look at, again, 1D versus 2D, just a quick example. If we have a truck carrying some brine, so some, salty solution at a given concentration, and let's say it's spread over 450 square foot, right? If the truck breaks and now there's a spread over some area, there's a thin aquifer underlying and velocity of 1.23 foot per day. What is the maximum concentration after 133 days? And you are given dx and dy, right? dx is 7 feet squared per day, and dy is 0.1 dx. So dy is 0.1 dx. I'll go back to this scaling between the x and y direction dispersion coefficient. So typically we take 10% if we don't have any other information. We just take the cross direction dispersion coefficient as just 10% of the main dispersion coefficient. And again, if we used our newly given 2D equation, we find that the peak concentration, again, remember that the peak is just m over z 4 pi t, square root of d and d. Again, m over z, we can you can see that this is the same as concentration times area, just by looking at the units. So m over z as units of mass per length equals C0, mass per length cubed times area in length squared. Sorry, this is not very good, but you can see length squared and cube disappear, and we end up with mass per length, which is the same as this. Okay, so if we look at the equivalent 1D version, right, so if we use mass divided by area square root of 4 pi dt, crunch all the numbers, you can see that the maximum concentration is about 10 times more for the 1D model than it is for the 2D model. Now, again, a note on the dispersion coefficient. So for groundwater problems, typically the dispersion coefficient, we actually use a dispersivity, and dispersivity is that alpha number, and this is in meters, right? So typically what we're saying here is that the dispersion coefficient is proportional to the velocity, right? The actual velocity, the linear velocity, so let's call that v of x, times some length scale, right? And a length scale that's given by alpha. Again, think of the unit dispersion is in length squared per time. Velocity, of course, is the length per time. So alpha, the dispersivity, is a length scale. Now, if we look at tabulation or a plot of data, right, the measured alpha versus a scale and dispersivity. So dispersivity, you can see if we plot or if we make a fit, right, if we fit a line through the data of longitudinal dispersion versus scale, we can see that alpha scales as 0.1 of x being the distance, right? So there's a scaling problem, right? So meaning the apparent alpha grows as the distance from the origin grows as well, or the distance. Remember that representative volume problem that I've talked about before? It's the same concept here, except basically what we're saying is there's no average alpha, as we grow. Instead, alpha keeps growing as we increase the x, the scale that we're looking at. So if we fit a line, it's 0.1x, so that's a good way, an easy way to find alpha for practical problems. And again, I'll give an example in a second. However, you can see here that, this line obviously is not a very, very good fit to the data, and the data looks like it's more like a log, right? Like a log trend. So if we want to fit, through a log, we can use, instead of just 0.1x, which is the easiest one, we can just use this equation here. I forget the authors of the original equation, but anyways, 0.8 log of the length scale to the power of 2.4, and that gives typically a little better approximation of the dispersivity. And then again, I already mentioned that, but the y direction, right? So we calculate the x direction dispersion coefficient as, say, the velocity times alpha. Alpha is calculated either using, this or that. Then that gives us dx, and then we just take the assumption, again, if we don't have any other information or if nothing else is given for that aquifer, we just take the cross direction dispersion coefficient as 10% of the x direction. So that's a practical way of calculating, back of the envelope calculations for the dispersion coefficient. Okay, in the next video, I will show you a very simple Excel model using the 2D and 1D advection dispersion equation, and just showing you the different scaling for the peak. And then after that, we move on. Thank you very much.